Come on. Okay. All right. So this will be the last portion of a class that might be a review for some of you, like those of you who took 561 last spring. If it's going to be all new stuff after that. Don't forget, today is when the quiz, the Canvas quiz on Chapter 3, the concept check questions are due, and then the regular homework problems and explorations on this chapter, those will be due on February 8th. Okay. Now, to set stage for today's material, all right. Now, we have methods for solving AX equals B for a general case and for certain specific situations, but we need to also analyze, be able to analyze the accuracy of these methods. So for such analysis, and also for a great many other situations, we need some way of describing the magnitude of vectors and matrices that play the same role as absolute value for numbers. So for vectors, you would have had a notion of magnitude that you would have seen in calculus. So the magnitude of a vector in that sense, which depending on the book, some books would write this using a double bar, which is what I prefer. Others use a single bar, just like absolute value. Where you just take the square root of the sum of squares. Okay. Okay. And this is a case for a real valued vector in a n-dimensional space. So we always have that to fall back on. But it's not the only one. And we're going to learn about some others. And we don't really have anything for matrices. Now, there is a natural choice for matrices where it's something like this, where it's just applied to all the entries of a matrix. You're taking a square root of sum of squares of all the entries of a matrix. And that is one that we'll see. But again, there are other ones that are useful too. So we're going to talk about notions of magnitude or norms for both vectors and matrices. Okay. Okay. I'm trying something a little different here. I've done this in other classes, but okay. In a way, to as an approach to slowing myself down. Okay, so as I said, we need to be able to measure error wherever quantities involved are vectors or matrices, and and we want to be able to have one number that describes it. So it's even though a vector or matrix has several components, and we can always look at the error in each component, we want to be able to look at the size of a vector or matrix as a whole. Okay. So first we're going to do vectors, and then we'll generalize that to look at matrices. Okay. So how are we going to generalize absolute value? Absolute value has certain properties that are well known, such as like the triangle inequality, and we want to have functions of vectors that yield a magnitude, and that should satisfy the same kind of conditions as absolute value. So now I can give the formal definition of a function called a vector norm. So whatever we're taking the norm of, it's enclosed in double bars, and we'll assume real valued vectors, but this will apply to complex also with appropriate generalizations. And the result is always going to be a real number, regardless of whether the vector itself is real or complex. So what does a function have to obey in order to be called a norm? So first of all, the norm has to be a non-negative real number. It makes no sense for distance to be negative. And the only time it should be 0 is if a vector itself is 0. So often, if you have a function that might be a norm and you're not sure if it is, a way to check is it possible for it to be 0 if x is non-zero? If that's the case, then it would not be a norm. Okay. If you scale the vector by a constant, then that should scale the norm by the absolute value or magnitude of that constant. Okay. And then the last one is the triangle inequality, that the norm of a sum must be less than or equal to the sum of the norms. Okay. Okay. So when n equals 1, we can just use absolute value. It would be that exactly, just for numbers. Okay. Now, there's a whole family of vector norms that are known to satisfy all of these properties. Okay. So we're called the P norms, also known as the LP norms. And here's the formal definition, where we take the absolute value of all the components, raise it to the pth power for whatever p is, sum them up, and then take the pth root. So the exponents here have to correspond to one another. So p here, 1 over p here. So we have that here with a case of p equal 2. So here's some p norms. All right. So regardless of what p is, it's a norm. So here are some particularly useful p norms. First, the 1 norm. And all of it is, that's just the sum of the absolute values of all the components. And then the P2, that's the one I showed you earlier. So that's also known as the Euclidean norm because it would give you Euclidean length. Now, when x is a real or complex vector, that's the same as x Hermitian transpose times x, and then you take the square root. So this is basically an inner product of x with itself, and then you take the square root. I don't remember if I actually covered Hermitian transpose before. So I'll give that here. I know I've talked about transpose. All right, so a Hermitian transpose, XH, is where you take the regular transpose, so like a row becomes a column and vice versa, and then take the complex conjugate. This is important because if you have some formula involving real vectors that uses a transpose, and you want to generalize it to a complex case, generally that means you have to change any transposes to Hermitian transposes in order for it to work in the complex case. That's actually why I have absolute value here. You might think, oh, why do we have the absolute value if we're squaring a number that is positive anyway? Well, we don't know that if you have a complex number and you square it, it's not necessarily going to be a positive real number. So if we take the absolute value, so it's squared, so it's the complex number times its own conjugate, then yes, it will be a positive or at least non-negative real number. Okay, so that's the 2 norm. And then if you let p go to infinity, we have the infinity norm. And all that is the absolute value of the largest element of a vector. The way to think of it is, as you let p increase, then the whatever's the largest entry ends up making a greater and greater contribution to the overall norm. So in the limit as p goes to infinity, the largest element is the only one that makes any contribution at all. So that's how we get this formula here. All right, so as an example, if I have this vector, 1, 2, minus 3, then I can go ahead and compute various norms. So here we have a 1 norm, so we just add up the absolute values of all the components. And then Euclidean length. And then the infinity norm, that's just going to be 3 because that's the size of the largest element. Notice, now square root of 14 is, oh, dang it. All right, so that is approximately that. So as p increases, the norm decreases. So that's true in general. So it'll converge all the way to the size of the largest element, which will just be 3. Okay. This one is specific to the 2 norm. One helpful property, which is useful in certain proofs. Hint, hint. Okay. So the 2 norm satisfies what's called the Koshi-Schwarz inequality. Okay, that should be. Oh, okay. If this is for real vectors, it would be x, h, y if vectors were allowed to be complex. For simplicity, I'm just going to stick to the real case here. This inequality I've also seen called the Koshi-Schwarz-Boniakovsky inequality. So maybe Boniakovsky is someone who came across it independently of Koshi and Schwarz. As I've mentioned before, it's kind of funny how people's names get attached or not attached to things like this. Okay. This is helpful for showing that the 2 norm satisfies the triangle inequality and therefore, in fact, is a valid norm. I want to mention that it's a special case of this more general inequality called the Helder inequality. That if 1 over p plus 1 over q is equal to 1, then we have its upper bound in terms of the p and q, p norm of x and the q norm of y. So we just set p and q equal to 2, and we get this. So So I'm going to show you how this is proved. Okay. All right, so we're just going, for simplicity, it's going to assume everything is real. So suppose I make this vector, x minus c times y, where c is some scalar. Then the dot product of this vector of itself, so x minus cy transpose x minus cy, that would be the 2 norm of x minus cy squared. Now that's the norm, therefore it must be non-negative. Also, in this case, we know it's the square root of sum of squares, so it must be non-negative for that reason. So now we use some properties of the inner or dot product. So this is non-negative, but now if I expand this, it's basically I'm foiling this out. So I have x transpose x and so forth. And I get all these terms. Now, c is a constant factor, a scaling factor, so I can pull it out of these. And dot product for real vectors is commutative. So x transpose y equals y transpose x. So these terms I'm actually allowed to combine. And then here I have c squared y transpose y. So x transpose x is a 2 norm of x squared. Y transpose y is 2 norm of y squared. So now I want to find c that makes this whole expression as small as possible, because this is a quadratic function of c. So I can just go ahead and take the derivative. So I take the derivative of this. Here we have no c at all, so that part gives us 0. And then I have minus 2x transpose y. Then here I have 2c times this equals 0. So now I can rearrange and solve for c. So now I can take this value of c and substitute it in here. All right, so that's what I had before. That's known to be non-negative. Now I go ahead and take a value of c that I have, substitute in here, because it's non-negative no matter what c is. So it's certainly true at the minimum also. So now I can simplify this. And what will happen is these two terms will actually combine. As I simplify a little bit, and now it's, oh, there's a typo there. That should be, oh God, if that's in the book, I'm going to be so pissed. I'll just check. Okay. Yes, I'm going to check it now. Yep, typo in the book. Okay, the new Python edition has just come out. Okay, and also there should be a subscript of 2. Okay, I think what may have happened, I may have been proving this in some other setting for a different class and copied it over and adjusted it, and I did not adjust everywhere. So these two terms combine with a coefficient of -1. Okay. And this is what we have. And this is greater than or equal to 0. So now I can just rearrange. And I get this. And I just take a square root of both sides. And that is exactly the Cauchy-Schwarz inequality. And I'm done. Are there any questions about how that unfolded?
I have one question.
Yep.
Can you scroll back up a little bit to the beginning of this part? Okay, yeah. From 0 is less than or equal to blah, blah, blah to the next line, how come it's less than or equal to there just carrying out foiling or?
Oh, well, no, because this is exactly equal to this.
Right. Oh, okay. I guess it's either or. Okay.
Yeah.
Like, why wouldn't we just write equals?
Well, we don't know what it's equal. Oh, I see what you're saying. So in other
Yeah.
words, okay, there are two conventions about this, saying that because this is equal to this, I should write equals. The other school of thought, which is what I subscribe to, is well, this whole thing is greater than or equal to 0. Therefore, this, which is the same thing, is also greater than or equal to 0.
Okay, so it's just preference and.
Yeah, and the idea is because there's a relationship between the left side and whatever is happening on the right side is being morphed, but this is always meant to relate the right side to the left side, not these steps to each other. And so that I do get what you're saying, and yes, there are some mathematicians who do follow that. It might be more appropriate if this was written like horizontally, because then it's easier to see how this is being related to this. But the idea is whatever we have here relates the sides and describes the relationship between them.
Gotcha.
Okay.
Thank you.
Okay. Other questions? Okay. So I'm gonna make a quick note about this typo because I have a running list, and sadly the list is still growing. And all right, so let's deal with those for whenever the second edition that comes out some years from now. Okay, so that's Cauchy-Schwarz proof. Okay. Now, I want to talk about norms and convergence, and how we define convergence of vectors, limits of vectors as opposed to limits of numbers that you'd be familiar with, like a calculus or real analysis. Okay. So the idea is, if we have some vector norm, any vector norm, then we have a natural notion of distance between them. So just the norm of x minus y. So now we can use that to define what it means for a sequence of vectors in n-dimensional space to converge. So here we have a sequence where the superscript k in parentheses, and the parentheses are important here, indicate index within a sequence. So I have x1, x2, x3 is converging as k goes to infinity. Okay. If so it converges to a limit x if the distance between xk and x, which this distance is now just a number. So now, and we know how to define limits of numbers, so that limit must be 0. Okay. Now, it doesn't matter what norm we're using to define convergence. But it turns out that if xk converges to x in whatever vector norm, each individual component of xk must converge to the corresponding component of its limit x. So convergence happens for vectors as a whole and component-wise. And the reason why that is true is because of one of the key properties of a vector norm, that the norm of a vector is 0 if and only if x is a 0 vector. In other words, all of its components are 0. If this difference is going to 0 in a norm, then the vector itself must be converging to the 0 vector. Therefore, each one of its components must be converging to 0. Therefore, we have this. Now, one of the nice things about norms and convergence, what if we know that a sequence of vectors converges to a limit x in a particular norm, like the one norm? It's natural to ask, well, does it converge in other norms to x? Or what if it doesn't converge in some other norm? What if it converges to something else? Is that actually possible? Or we could have different convergence scenarios depending on what the norm is. And thankfully, the answer is for essentially no, especially for p norms. If a sequence of vectors converges in a certain p norm to a limit x, it must converge to the same x in any other p norm. And this leads to the notion of what are called equivalent norms, which may have also come up in certain other classes, possibly, like maybe 771. So we say that two norms are equivalent if one of the norms is bounded both below and above by certain constants times the other norm, where the constants C1 and C2 cannot depend on x. So if that's the case, for certain constants C1 and C2, we say the norms are equivalent. So that way, if we have a sequence of vectors that's converging to 0 in the beta norm, for instance, it must converge to 0 in the alpha norm also. It's basically the application of a squeeze theorem. So all p norms, one norm, two norm, infinity norm, any other p norms, all equivalent. Okay. Here are some relationships between specific norms. For instance, the one norm is always greater or equal to the two norm. Two norm is always greater or equal to infinity norm. That's why I mentioned as p increases, the norm decreases. And if x is in Rn, one norm is less than or equal to square root of n times the two norm. So if this is independent of x, it just comes from the dimension of a space. Now, I won't go through the details here. I'm just going to include in the notes how this can be proven. Like showing that the one norm and two norm are equivalent. So if you want to look at this later, here's how that would go. Like if you could show that this relationship holds, and like how to actually find the constants C1 and C2 that work for the whatever norms you're working with. Okay. All right. Okay. What I'd rather talk about, which is very important for us, is matrix norms, which you're going to need that for studying the accuracy of AX equals B, and also its sensitivity. All right, so we want a notion of magnitude of matrices, but it's tempting to just take the matrix and like reshape it into a vector and use vector norms. But we're not going to go that way entirely. And that will be one example of a norm, but what we're going to do instead is we're going to define a matrix norm in a very similar manner to vector norms. So it's a function from space of m by n matrices to real numbers. So technically, each size of matrix has its own norm. Okay, first, these first three properties are exactly the same as for vector norms. That it's 0 if and only if a matrix is 0, otherwise it's going to be a positive real number. We scale the matrix, it scales the norm by the absolute value. We have a triangle inequality. And then there's one other property that, depending on the book, may or may not be included in the definition of a matrix norm, but it is a property that most matrix norms satisfy. It's called the submultiplicative property. So if you have two matrices for which it makes sense to multiply them, then you have this property that the norm of AB is less than or equal to norm of A times norm of B. Which is particularly nice if A and B happen to be square matrices. And this is very helpful to use for certain proofs involving matrix norms. So how do we define a matrix norm? It's a little tricky. If you have a vector norm already, you could define a matrix norm from it. So if it's defined for, if you have m by n matrices, so you have the appropriate vector norm for m vectors and n vectors, then I could define a matrix norm this way. It's the supremum, or the least upper bound. Apologies to anyone for a real analysis flashback. Of the vector norm of AX divided by the vector norm of X. Equivalently, it's the maximum over all unit vectors of magnitude 1 of A times X. So the idea is, if you multiply the vector X by A, how much is the norm of that vector amplified? The maximum possible amplification is the matrix norm. I want to point out the reason why we have sup here and not max. The maximum of taken over all unit vectors, instead of all unit vectors, is a compact set. A continuous function on a compact set has a minimum and maximum. Instead of all non-zero vectors, not a compact set, not guaranteed to have a maximum over such a set. Okay, so this is how we have a induced matrix norm coming from any vector norm. So for any vector P norm, the ones I just defined earlier, you could define a matrix P norm using this. And it's been shown that if you have a vector P norm, the induced matrix norm does satisfy the submultiplicative property. So we can just go ahead and take that for granted in such cases. So here's some matrix norms. Okay. Okay. So taking the P norms mentioned earlier, we can define matrix norms. So the one norm, or L1 norm of a matrix. Now it's defined from here, but then this formula comes from actually trying to evaluate this. It is it's the maximum row sum. So sorry, that's absolutely wrong. Column. It's the maximum column sum. All right. So what am I doing here? Notice in a sum, I is changing, J is not. So I'm taking the sum of the absolute values of all entries in column J. Then I'm taking a maximum of that over all column indices J from 1 to n. So whichever column has the largest sum of the absolute values of its entries, that value is the matrix 1 norm. Okay. So taking the absolute value of all the entries, taking the maximum column sum. Now, I do have worked out here the proof. Again, because of time, I'm not going to go through the details of it. It comes from using the definition of matrix vector multiplication. So here we have one component of A times X. We write it out in terms of the matrix vector matrix vector product formula. Then triangle inequality just applied to ordinary absolute value lets us move the sum outside the absolute value, and then we pull the x's out. So basically, we're rearranging the order of the sums. And what do we have here? This is a column sum. So it's certainly less than or equal to this times the maximum column sum. But x is assumed to have a one norm of 1. In other words, the sum of all the absolute values of the entries of x is 1. So we see that one norm of A times x is less than or equal to the maximum column sum. Now, the second part of a proof is to find a specific x for which one norm of A times x equals this. That's how you can show it's not just an upper bound, it is the least upper bound. So here I pick a specific x, it's a certain column of identity for which this formula happens to be equal to the one norm of A times this specific x. Because multiplying A times this vector E capital J, this is a capital J column of identity. So A times this vector is just a capital J column of A. All right. So that's how you prove formulas for norms. You find an upper bound for the norm of A times X. That hopefully would be your formula. And if you can show that for some X, this is inequality is an equality, then it's proven. I mean, infinity norm, very similar. That is the maximum row sum. Notice in this sum, J is changing, I is fixed. This takes the sum of the absolute values of all entries in row I, and then we take a maximum of those, and that's the infinity norm. The proof that this is a formula has the same template as the one for the one norm. You just have to, using similar properties of matrix vector products, and a different vector here would need to be used to show equality for a certain x. Okay. So these two matrix norms are pretty easy to compute. That we're just performing some additions and also some comparisons to find which column sum or row sum is a max. Now, what about the two norm? Now, that's from a definition of an induced norm, but what about an actual formula? That's actually harder to come by than in the case of a one norm and infinity norm. So a two norm is much more difficult to compute. So if I define this function g of x to be this fraction, norm of ax divided by norm of x, and you take the two norm and square it. Well, based on the formula for a vector two norm, that would be ax transpose times ax, which gives us this. And this would be x transpose x. Now I can try to find, I need to find where this is maximized. So I can try to find a maximum. So if I were to take the gradient of this function, which I won't take the time to do here, but if you did, and set it equal to 0, then this function G is a local maximum whenever this is true. And notice we have A transpose times X equals this quantity, which is a number, times X. What does that mean? That's the same as saying that X must be an eigenvector of A transpose A, and this is the eigenvalue. So that actually gives us a formula for the matrix 2 norm. If this is maximized whenever X is the eigenvector for the largest eigenvalue of A times X, or should say the largest eigenvalue of A transpose A. So that's the 2 norm. We take the largest eigenvalue of A transpose A, and notice since this is squared here, we got to take a square root. Now, that's not something that can be computed as easily as these other norms, the 1 norm and infinity norm, where we're just taking sums. So in MATLAB, for instance, if you're going to use matrix norms, if I were to use a 1 norm or infinity norm, this would be more costly. Okay. Okay. That's one thing that's kind of unfortunate, that these vector norms are all easy to handle, but not true for matrix norm. There's one more norm for matrix norm that is straightforward to compute, a Frobenius norm. And that is as a subscript F. And this is just, oh, I should put absolute value here. Okay. Okay. Well, not necessarily if these are real matrices, but anyway. So now a Frobenius norm, not a P norm. If you took a matrix A and you reshaped it into a vector of size m times n and took its vector 2 norm, then that would give you a Frobenius norm. So it is a valid matrix norm, it just doesn't relate to any P norm. But it's a lot easier to compute than the matrix 2 norm. Now, matrix 2 norms are also equivalent to one another. So here are some relationships between, for instance, a Frobenius norm and a 2 norm, or a 2 norm and an infinity norm, or a 2 norm and a 1 norm. So the sequence of matrices that converges in some norm will converge in the other ones. So as an example, here's my matrix A. So the 1 norm, we just take the column sum. So here's the sum of a first column, sum of a second column, sum of a third column. The largest such sum is 7. In infinity norm, we look at the rows. So here's first row sum, second row sum, and third row sum, and the largest such sum is 6. So that's the infinity norm. If I took a square root of sum of squares of all of these entries, that would be the infinity norm. So that would be fill in the non-zero entries. Okay. All right, so we have 13, 14, 15, and 16 is 31, square root of 31. So that would be, ooh, that's kind of freaky. 5, 6, 7, 8. Okay. Questions about matrix norms. So to put this okay. The 2 norm, I just had MATLAB compute that. So we get a smaller value there. So here's computing the square root of the largest eigenvalue of A transpose A. Okay. Now what we're using all this for is to understand the sensitivity of a problem solving AX equals B. That takes us to the condition number. So if A changes or B changes, how does that change the solution X? Now, if A or B change by a small amount, can we be sure that X only changes by a small amount? Or can we have some idea of how much it changes? So to that end, we look at this parametrized system. So when epsilon equals 0, we just have AX equals B. But A is perturbed by matrix capital E. Vector B is perturbed by this vector little e. So X is now a function of epsilon. So X of 0 is just solution of AX equals B. Okay. So all right, so if I define R to be this quantity here, if I choose epsilon to be small enough, then this norm this norm will be 1. Okay. And that helps guarantee that this system actually has a solution for whatever choice of epsilon I have. So I want to look at the relative change in X. So X epsilon minus X divided by the norm of that divided by the norm of X. Now, okay. Oh, something about got Biscuit agitated. Okay. Anyhow, okay. Actually, I want to show you. So a solution, where this line comes from, is X is equal to A inverse B. And for this parametrized system, I have A times x of epsilon equals, and then I can rearrange the right-hand side, b plus epsilon e minus epsilon, capital E, x of epsilon, so then I have x of epsilon is going to be A inverse times all of this. Okay. So then x of epsilon minus x, I'll have an A inverse term in both, which will then cancel. And what's left will be A inverse times all this, which is what I have down here. So that's where that came from. Now, I can use a submultiplicative property of norms. Oh. Okay, hold on. Oh, okay. What I did here is I did an add and subtract trick. I subtracted A inverse EX and added it back in. So then I could break these up. And according to this. Triangle inequality, I can split these up. And okay. Into these sums. And what I end up with out here is I have okay. Oh, I think I have a slight mistake here. Okay. Oh, wait. Yeah, that factored out. Okay. This epsilon should not be here. Because I already have it out here. Here I use triangle inequality to split these up. Here I have epsilon A inverse E. Well, the norm of that's defined to be R. So here I've used a submultiplicative property of norms, that the norm of this part is less than or equal to the norm of this matrix, epsilon A inverse capital E, times the norm of this vector. So as long as I have less than or equals, I can do that. And that's just R, how I defined it up here. Okay, I'll fill in intermediate step. Okay. Now, what I can do next is I can take this term, which is the same as this, except for a factor of R, move it to the other side. And then I can divide both sides by 1 minus r. And that's going to give me this. Okay. Now I break this up by triangle inequality. And I have norm of A inverse is pulled out because it's submultiplicative property, norm of E over norm of X. And then the same thing over here, wherever norms of X cancel out, and just have a norm of capital E. Then what I do is I multiply and divide by A and use the fact that A times X is B. So that means the norm of B is less than or equal to norm of A times norm of X. So then I'm going to have norm of A times norm of A inverse out here. When I divide by norm of A here, I have norm of A times norm of X in the denominator, which is, so when it's in the denominator, I keep my less than or equal to relationship here, and this becomes B. So what happens is the relative change in X is bounded by 1 over 1 minus R times kappa of A, which is the norm of A times the norm of A inverse. And that is called the condition number of A. And that's times the relative change in the right-hand side, so little e over B, plus the relative change in the matrix, so capital E over norm of capital E over norm of capital A. So whatever changes we made to A and B, it's the norm of those changes divided by the norms of what we're changing in both cases. So however much the system changed, that gets amplified by the condition number. So a condition number gives us a measure of sensitivity. That how much the solution changes in terms of how much the problem has changed. So if a condition number is large, that's bad. It's called ill conditioned, because that means the system may have changed only a little bit, but the solution has changed by a lot, and we definitely don't want that to happen. Now, here I assumed any matrix norm, doesn't matter which one. If we want to specify a norm, we use that as a subscript of the kappa. So kappa 2 of A is 2 norm of A times 2 norm of A inverse. Are there any questions about what happens to these manipulations? I know I've not included every single one. But.
So I'm a bit confused about how we moved from how we got to the 1 over 1 minus R.
Oh, here?
Yes, I'm not sure I can.
So I have this on the left side, and then the same thing times R.
Okay.
Move this term to the other side.
Okay.
Hold on. Dang it. Yes. I'm very busy. I'm giving class. This is not.
Okay.
Class right now. I'm very busy. You tell him, Biscuit. Okay. So this term gets moved to the other side. So now you have norm of X of epsilon minus X over X times 1 minus R.
Then we divide both sides.
Then you do, yes.
Okay. Okay, I get it.
Okay. Other questions?
I'm sorry. One more question, I think.
Okay.
So, from the next line, well, we had small e minus ex. So I assume we factored out A inverse, right?
Yeah. Yeah.
So why is that changing to a plus?
Oh, from here?
No. Well, we had A inverse multiplied by E minus EX. The line still on the line where we have 1 over 1 minus R.
Okay, hold on a second. Dang it. Okay. So, all right, so still here?
Yes.
Okay.
So, like, we'll move to the next line. We had E over X plus norm of E. So that should be minus norm of E.
Oh, no, because here triangle inequality was used. So the norm of this whole thing is less than or equal to norm of A inverse E plus norm of EX.
Does the triangle inequality work like that?
Yeah, it's always a plus.
I just for the triangle inequality to work, the inside has to be a sum, like A plus B. It's less than norm of E plus norm of B.
Yeah, except for one thing. Like, okay, so I could say this is less or equal to norm of A inverse E plus norm of minus EX.
Okay.
But then norm of minus EX equals norm of EX.
Oh, I see. Okay.
Okay. All right, so this is how we interpret a condition number. Relative changes in A or B are amplified by whatever condition number is in a relative error in the solution. I should make clear that is the relative error. Okay. Okay, so if a condition number is large, we say it's ill-conditioned, otherwise we say it's well-conditioned. The condition number is always greater than or equal to 1. So that's the best you can hope for. Like the condition of identity is 1. Now, a condition number is hard to compute because that involves computing A inverse, which is difficult. So that's one problem. That we could get an estimate, that would be fine. Cond, the MATLAB function cond, can compute the condition number. And if you just say a cond of A, that would use the 2 norm for a condition number, but you could also specify a different norm. Okay. Now, as an example, okay, about the effect of conditioning. I have some sample matrices here that just by eyeballing it seem to be pretty close to one another. This matrix is well conditioned, condition number of 10. One on the right, ill conditioned. It's on the order of 10 to the 8th. So you can't really tell condition number so much just by looking, except in certain very special cases. Now, what does this mean when solving AX equals B? So I'm going to solve two equations involving A2. So I have right-hand side B1 and B2, and I get solutions X1 and X2. So here are my vectors B1 and B2. And so they're somewhat different, obviously, but not terribly different. There's about a 10% difference between them. But here's a solution using B1, gives us X1. Here's a solution involving X2 on the order of 10 to the 7th, so a ginormous change. So that's what ill conditioning can do to you. If you basically can't trust the solution that it gives you, and that's unfortunate because there's some matrices in important applications that are ill conditioned, and this sort of thing can happen. Now, a more geometric interpretation of a condition number is it's basically distance to the nearest singular, and I want to emphasize, I like to say singular or non-singular. Singular means not invertible. So in other words, if A is ill-conditioned, that means a nearby matrix is singular. Now, you might think, well, we can tell if a matrix is singular by looking at its determinant. So why not just use a determinant to measure near singularity? It's actually not a good idea. A matrix can have a large determinant, but if it's ill-conditioned, it's close to being singular. Or a matrix can have a very small determinant, like near zero, but it's actually well-conditioned. So the determinant of A, while it's zero if and only if singular, doesn't give a notion of distance from singularity. And as an example, I'll show you this matrix that has this strange pattern of ones and minus ones. But it's upper triangular, so the determinant is just a product of the diagonal entries. The determinant is 1. The condition number is nearly 2,000, so it's not very well conditioned. But the determinant is nowhere near 0. But A is still close to a singular matrix. So in fact, there is a singular matrix that's this close to A. Oh, let's build onto another page. So that's why we use a condition number to gauge distance from a non-invertible matrix, not the determinant. Okay. Unfortunately, we only have a little time left. Does anyone have any homework questions?
Not a homework question. You said singular was invertible or non-invertible?
Not.
Not. Singular is not invertible. So non-singular is invertible.
Yes.
Okay.
Okay.
Sorry, no, I just sneezed and said okay at the same time. It was really awkward. All right.
I still need help with 341. I've done all 3 points, which I would like to show you. I don't know if I can do that.
Oh, okay.
Maybe after class.
Okay. Just want to see if I have any preemptive hints in case anyone else is having trouble with that. Okay. Well, I'm gonna type something in here about this problem. Okay. Or I think I don't know if I did it before. Okay. All right. So, actually, this part I think I said before. All right. So we show that A plus epsilon E it should be a epsilon, and there it is. And for some non-zero x. All right, I will go a little further. Okay. All right, so then just rearranging, I have this. But then I can rearranged again, multiply both sides, we're assuming at least A is non-singular. Okay. Now we're dealing with a specific type of norm. We can assume any norm. If we take the norm of both sides of this, okay. Then properties of norms I've been talking about today can be used to arrive at a contradiction. Because we're assuming that the norm of this matrix, epsilon A inverse E, that has a norm less than 1. And if you show that we get some sort of contradiction there, then that would prove that A plus epsilon E is non-singular after all.
So one show, we're assuming that this is less than 1, right?
You have a norm, yeah.
So I'm not sure because so I worked it out and I got something like I got something like the norm of that to be greater than -1. I don't know if that's a contradiction.
Yeah. Something went wrong there because when you're there shouldn't have been a negative, because things when you take a norm of both sides, then the minus ends up not mattering because the norm of x is equal to the norm of minus x.
Yeah, so because if we are assuming x to be non-zero, then the norm of x must be greater than 0, right?
Yep.
Yeah, so somehow manipulation, because we have greater than 0 on one side, when I do the manipulation, I end up getting -1, and that's what I'm very, very confused about. Okay. I don't know if it's possible to meet maybe sometime tomorrow during your office hours. I don't know. We've not really given us a fixed office hour. So I can show you.
Well, there's always Tuesday, Thursday at 4. I can. So that's my announcement of official office hours. Okay. That I'm always available during that time. But just keep in mind
what I've done, and then we can figure out what I did wrong.
Yeah, because so just in general, when once you take the norm of a vector or matrix, if there's a minus multiplying the expression, just drop it. Because it doesn't change anything anyway once you take the norm.
Okay. So, but if we do this, are we going to get it greater? I was thinking that we do this, we're supposed to get equal to something. So is it going to be an equal sign or or an inequality? I'm not. That's the only thing I'm confused about.
Well, once you end up using any properties of norms, like for instance a submultiplicative property, that will change the equals. It's an equals now, but it'll change to a less than or equal to.
Okay. Okay.
Yeah, and that's going to be the key to establishing a contradiction.
Okay. Yeah. Thank you.
All right. Okay. Well, unfortunately, we're already run past time, and as several of you know, I have another class coming up right now. So I will see those of you there, and then okay, and hopefully I'll be ready for that. Okay, so I'll stop recording at this point, and so you get to scram for a few minutes.